Hello and welcome. In this video, we're going to be taking a look at a particular kind of optimization technique for functions of multiple variables. Specifically, we're going to be looking at absolute extrema. So that gives us the absolute maximum and the absolute minimum. We're going to be looking over a particular type of region. So why don't we start off by maybe just reviewing the difference between local extrema and absolute extrema. Now, we've seen this in a previous video already. A local extrema is where we have maybe the function evaluated at some point p naught be the smallest or largest value in a region around that point. For any other point close by, f evaluated at p naught is either the biggest or smallest. That gives us a local extreme value. An absolute extreme value is where the function evaluated at some point is the biggest possible value over the entire domain of the function, or potentially the smallest possible value over the entire domain of the function. And that's what we're going to be focusing on in this video. Now, the extreme value theorem is something we've heard of before in single variable calculus. We need to have a continuous function over some closed interval. But now that we have a function of multiple variables, we're going to have a slightly different wording to that same theorem. Here we're going to let f be, again, a continuous function, no change there, but over some closed and bounded set D in n-dimensional space. That's quite different from our closed interval. Then, just like the conclusion of the extreme value theorem from single variable calculus, we are guaranteed that f attains an absolute maximum and minimum value at some points in that set. So why don't we take a look at these two words here, closed and bounded sets. Let's start off with the term a bounded set in Rn. Put simply, this means that that set can be contained within some ball of finite radius. Now, this is a ball in n-dimensional space. So actually, if we're talking about R2, that ball is a circle. In R3, that's a sphere. But in higher dimensional space, a ball is just a set of points that are some fixed radius from a particular center point. In another way of putting that, we could say that D consists of points, x1, x2, all the way to xn, such that each of those points is less than some distance d from the point a1, a2, all the way up to an. This is our distance formula. Essentially, we're saying that this region D cannot extend infinitely in any particular dimension at all. Now, as for a closed set in Rn, this is just an even further restriction on that. This would imply that the set D also includes all of the points along its boundary. For example, if we were looking at two-dimensional space, then we could have a disk, which is definitely going to end up being a bounded set. But it could either include its boundary or it may not include its boundary. If it does include the boundary, then we would say that that disk is both closed and bounded. With a closed bounded set, the extreme value theorem says that we get an absolute maximum and minimum value. So let's see about finding those extreme values. Just like the closed interval method from single variable calculus, we have a very similar process here. To find extreme values on that closed and bounded set D, we're going to start by looking for critical points on the interior of that set. Critical points would be where the gradient is equal to the zero vector, or where the gradient of f is undefined, or does not exist. Next, we're going to look for critical points that are along the boundary of that region. We'll also need to take a look at finding the vertices of that boundary. And what we'll do is we'll take all of the critical points on the interior and on the boundary, as well as all the vertices, plug them into the function, and we can figure out which of those points gives us the absolute maximum and which of those points gives us the absolute minimum. Why don't we take a look at a couple examples? We're going to be focusing on functions of two variables, and that means that this region is just some region on the xy plane. And we can take a look at regions with various different shapes as well. In each of these examples, we're going to find the absolute maximum and minimum values of the function for whatever the given region in R2 is. Here is the function 2y squared minus 4xy plus 4x. And let's suppose we're looking at the region T T for triangle. This is going to be a closed triangular region that is defined by three vertices. 0, 0, the origin, 5, 0, and 0, 5. So we could maybe just quickly sketch that triangular region. All right, here you can see are those three vertices, and our region is bounded by three straight lines. I've just color-coded those three straight lines here with blue, red, and green. Let's start off by looking for critical points on the interior. Within that purple shaded region, we're going to be trying to find solutions to the equation where the gradient of f is equal to the 0 vector. It doesn't look like we're going to get any other critical points of the form where the gradient of f is undefined, since we're dealing with a polynomial here. Now that equation can be broken down into two pieces. Firstly, we can take the partial derivative fx, and that's equal to negative 4y plus 4, set that equal to 0. And next, we can set the partial derivative fy, which is 4y minus 4x, equal to 0. And then we'll start solving these two equations. Now, the first equation is much easier to solve than the second, so let's work with that. That first equation we see has the solution y equals 1. And we can plug that into our second equation. Substituting y equals 1 into our second equation, then we have 4 minus 4x equals 0, and that gives us x equals 1. So right away we have one interior point, and that is the point 1, 1. Now that we've got any critical points on the interior, let's take a look at one of these boundaries. Why don't we start off with the blue boundary? Now for that vertical line, we need to have the equation of that line. And because this is simply the y-axis, the equation of that blue line is x equals 0. Now we plug that into our function. For the boundary where x equals 0, then we can simplify this function along that boundary to f of 0, y. That replaces all of the x's with zeros, and that just gives us 2y squared. Now, you can see how this is really just a function of one variable. If you like, you could call this function g of y. Now that function is only going to be useful along an interval for y. If we take a look at this blue line segment, y is only going to be from 0 to 5. We only need to look for maximum and minimum values along that interval. Now hopefully this should sound familiar. Looking for extreme values of a single variable function that is continuous on a closed interval. Or actually just right back to the extreme value theorem from single variable calculus. And with the extreme value theorem on a closed interval for a single variable continuous function, we look for critical numbers. In this case, we're going to be looking for where the derivative, this is g prime of y, and that's 4y, equals 0. By solving g prime of y equals 0, we end up with the equation 4y equals 0, and that gives us one critical number, y equals 0. But that's a critical number of the function g of y. That actually gives us a critical point that we're going to be looking at along the boundary where x is 0 and y is 0. Now that also just happens to be one of the vertices. Now let's not forget that when we are using the closed interval method for a function of one variable, we also have to consider endpoints. This 0, 0 is already one endpoint of that blue line segment. It's one of the vertices of the triangle. But we can't forget that we might end up with a maximum or a minimum value of the function at the other vertex, which is 0, 5. That means that there are two boundary points to consider. And we're up to 3 points in total now where we might get our absolute extreme values. We have 2 more boundaries to work with. Let's look at this red line for the bottom boundary. Since that bottom boundary is the x-axis, it has the equation y equals 0. And along that boundary, we can just substitute y equals 0 into our function. F of x comma 0 is just 4x. And you can see how that is really just a single variable function. We could also call that just g of x if we like. And the interval for x along that line segment will be from x equals 0 to x equals 5. We'll use the closed interval method of this single variable function on that interval since 4x is continuous. However, g prime of x is just equal to 4. That will never equal 0 And that means that we have no critical numbers on the function g and no critical points of our function f along that boundary. However, we can't forget to include the vertices here. We've already got the left-hand vertex, 0, 0. That just gives us one additional boundary point at the location 5, 0. Now, there's only one more boundary to take a look at, and that's this green line. This time around, it's not just a horizontal or vertical line, but we can easily figure out the equation of the line because we have the y-intercept, which is 5, and a slope, which is going to be rise of -5 over run of +5. That gives us a slope of -1. So the equation of this line is y equals 5 minus x, or -x plus 5. We're going to go ahead and plug y equals 5 minus x into our function. That will give us 2 times 5 minus x squared minus 4x times 5 minus x plus 4x. Probably best if we just go and expand that thing out. And again, we'll have a function of one variable, so we might as well just call that g of x for the time being. And once again, our interval here for x this time is going to be from 0 to 5. Even though it's a diagonal line, at the beginning of the diagonal line, x equals 0, and at the end of the diagonal line, x is 5. Okay, we might get some critical numbers here. Let's set that derivative equal to 0. Set the derivative 12x minus 36 equal to 0, we get the value x equals 3. Now, this time around, we also have to compute the y value. It's not just along a nice horizontal or vertical line. We actually have to plug that value x equals 3 back into the equation of this diagonal line, and that is y equals 5 minus x. Now, 5 minus 3 gives us 2. As for the endpoints, when x equals 0, we get y equals 5, and we've got that point included already. That was actually one of the boundary points along the blue line. And if we let x equals 5, we get y equals 0. That is one of the boundary points that we already got along the red line. There's only one additional point to consider here on our function f. That's the point 3, 2. Now we're finally ready to determine which of these 5 points might give us the absolute maximum, which gives us the absolute minimum. Might be best to make a little table of values here. We'll make a list of all 5 of these points and plug them into our function. Let's put these points in order, starting with the interior point 1, 1. If we plug that into our function, f of 1, 1 is just equal to 2. If we plug 0, 0 into the function, it's pretty easy to evaluate. Our function just equals 0. If we plug x equals 0 and y equals 5 into this equation, we're up to 50. And that looks like it might be our absolute maximum, but we have 2 more points to consider. If x is equal to 5 and y is equal to 0, we have 20, which is close but not quite the maximum. Finally, when x is equal to 3 and y equals 2, it's the only time we actually see the function get a negative value. So that must be our absolute minimum. We can just simply maybe state those 2 results. We get an absolute maximum value of 50 at the location of the point 0, 5 in the region T, and we get an absolute minimum of -4 at the point 3, 2 in that triangular region. Now, to get a better sense of what we've done here and the significance of these 5 points, I've actually plotted this function over that triangular region, you guessed it, in Maple. So let's take a look here. The way I've gotten around plotting this function over that specific region is I've made f of x, y a piecewise function, equal to the function 2y minus 4xy plus 4x, but only over the triangular region where x is greater than 0 and y is greater than 0 and y is less than or equal to 5 minus x. It's going to be undefined otherwise, and that means that we're not going to see the function anywhere other than over that triangular region. So let's go ahead and try plotting that. If we rotate around here, then we can see we end up with kind of a neat little shape. We have the triangular region if we look straight down, and we can see the x and y axes along the edges here. So at the point 0, 0, at one corner there at the origin, we can see it's actually a little bit of a local minimum. It's kind of just bending down there a little bit. At the point 1, 1, that was a critical point, but if we were to classify that with the second partial derivatives test, it looks like that should be a saddle point. But we didn't even have to worry about testing that point. We were going to be looking for absolute maximum and minimum values, not local extrema. Now if we take a look, we have one value here where we end up with a negative value for the function, and that is exactly where y equals 2 and x is equal to 3. And the highest 2 points that we see are at two other corners, 0, 5 and 5, 0, with the highest value at x equals 0 and y equals 5 up here in the corner. Now let's take a look at this second example and see what I've got in store for our next region. Our next function is g of x comma y, and it's going to be x squared plus 2y minus y squared. And this time our region is D, which is still actually just in quadrant 1. X must be greater than or equal to 0. Y must be greater than or equal to 0. However, x squared plus y squared must be less than or equal to 4. You might recognize that that boundary, x squared plus y squared equals 4, is a circle of radius 2. If x squared plus y squared must be less than or equal to 4, then we're looking at the region that's contained within the disk centered at the origin of radius 2, but only in quadrant 1. Let's see if we can just sketch that first. In quadrant 1, we're going to have 1/4 of a disk of radius 2 centered at the origin. We could put the vertices on here. We've got the vertex at the origin, 0, 0. We've also got one point here at 2, 0, and one point on the y-axis at 0, 2. Those 3 points are definitely going to end up being 3 values that we have to plug into our function g as potential extreme values. But we have 3 other boundaries. Once again, we have the vertical blue line here, x equals 0. We have the red horizontal line, once again, y equals 0. And then our green third side isn't a straight line. The equation of this curve is x squared plus y squared equals 4. So we'll have to figure out how we handle that kind of curve as a boundary. But first, let's start with interior points. Within that region D, we're going to be trying to find points where the gradient of g either equals the 0 vector or is undefined. But once again, we're dealing with a polynomial, and that eliminates the second type of critical point. We only need to consider where the gradient of g is equal to the 0 vector. Splitting that up into 2 equations, we can set g partial x, which is 2x, equal to 0. That gives us one solution, x equals 0. And then we can set g partial y equal to 0. That would be 2 minus 2y equals 0. That equation has the solution y equals 1. But if x equals 0 and y equals 1, that's actually on the boundary. That's right along the blue boundary here. We're going to see that we find that point again as soon as we deal with that blue line for our boundary. There's actually no critical points properly on the interior of this region. That's quite okay. That just allows us to get right to the boundaries now. Let's start off once again with the boundary along the y-axis when x equals 0. Letting x equal 0 in our function g gives us 2y minus y squared. Now we can treat that as a single variable function if we want. Why don't we call that function f of y this time? And our interval for y is only going to be from 0 to 2 this time around. Using the closed interval method on that single variable continuous function over that interval, we just need to find out where the derivative of f equals 0. 2 minus 2y equals 0 is the equation that we've already seen up here when we solved for when the gradient equaled the 0 vectors. And we got the solution y equals 1 already. So we're going to see that exact same point, 0, 1. But since this is a closed interval, we also have to consider y equals 0 and y equals 2. That gives us 3 boundary points in total. The origin, 0, 0 at one vertex, 0, 1, which is where the gradient of g does equal the 0 vector, and then one other vertex, 0, 2. Now let's move to the bottom boundary along the x-axis when y equals 0. If we let y equal 0 in the function, you can see that we end up with just x squared. That's a single variable function, and we only have to consider x values from 0 to 2. Once again, we'll take that as a single variable function and apply the closed interval method from single variable calculus. Critical numbers would be when f prime of x equals 0. That would mean 2x has to equal 0, and that gives us the solution x equals 0. However, if we have y equals 0 and x equals 0, we've already got that point covered. That's one of the 3 boundary points along the blue line segment. So that means that we only have to consider one other potential value, and that is when x equals 2. That gives us one additional boundary point at the point 2, 0. So we've got at least some repetition going here and only 4 unique points so far. But we have to deal with this final boundary, x squared plus y squared equals 4. And as you can tell, the goal has been to take that equation of one of the boundary curves, they were lines so far, but we'll need to substitute that into our function so that we can eliminate a variable, reducing the number of variables to just one variable, which is much easier to look at derivatives and endpoints. So why don't we take this equation, x squared plus y squared, and think about the best way of substituting that into our function. You might be able to guess that it's actually easiest to let x squared equal 4 minus y squared, and we'll plug that in, leaving us with a function only of y. Let's try that out. Along this particular boundary, x squared plus y squared equal 4, since we're only in the first quadrant, that means that x is actually equal to the square root of 4 minus y squared. But we know that x squared can be simply just replaced with 4 minus y squared. That will leave us with a function of just y now. X squared is replaced with 4 minus y squared plus 2y minus y squared. If we want to just collect terms there, we can treat that as the function f of y, single variable function that is continuous over the closed interval from 0 to 2. If we take a look at critical numbers of that particular function, we look at the derivative, 2 minus 4y equal to 0, and that gives us one critical number, y equals 1/2. Now this time around, because this isn't just a nice straight line where x equals 0, to get the x coordinate, we'll actually need to plug y equal 1/2 back into our equation for x. X equals the square root of 4 minus y squared. If that's the case, then x is equal to the square root of 4 minus 1/2 squared. 1/2 squared is a quarter, and 4 minus a quarter is going to be 15 over 4. We take the square root of 15 over 4, then at least we can take the square root of that denominator and leave us with the square root of 15 over 2. That gives us one more boundary point because the two vertices when y equals 0 and y equal 2 have already been covered as the two endpoints of that green arc. We simply just need to look at the point root 15 over 2, 1/2. Now we're ready to make a little table of values and see which of these points wins out as the absolute maximum and which one wins out as the absolute minimum. We have 5 total points to plug into this function. Along the blue boundary, we found 3 points, 0, 0, 0, 1, and 0, 2. Along the red boundary, we only had one additional point, 2, 0. And along the green boundary, again, only one additional point, root 15 over 2, 1/2. And that's ignoring any duplicates. Now, let's start evaluating function g at each of these points. As you can see, plugging 0, 0 in, the function g evaluates to 0. If we plug in the point 0, 1 into our function, then our function evaluates at 1. If we plug 0, 2 into our function g, then we end up back at 0 again. Hopefully that kind of makes sense, because along the boundary when x is equal to 0, it's just a parabola, and it is opening downward. So it just goes from 0 up to 1 and back to 0 again. Now along the red line, we have one more vertex that we haven't looked at so far, 2, 0. We plug that into our function, g of 2 comma 0 is equal to 4, which so far seems to be the absolute maximum. But we need to plug in the 1 point along the green boundary. It's kind of a weird point. But luckily, when we plug root 15 over 2 into x squared, we end up with 15 over 4. And we'll just plug y equals 1/2 into that equation, and adding fractions together, we end up with 9 over 2. And that is the largest value that we end up getting by a very small margin. That's 4.5. That means that we have a tie for the absolute minimum value of our function. If we want to state that, we will say that the absolute minimum of our function g is equal to 0, and it occurs at 2 points, at origin 0, 0, and also at the point 0, 2 in that region D. Finally, we have an absolute maximum value at that one other point. The absolute maximum of this case is going to be 9 over 2, and it occurs at the point root 15 over 2, 1/2. Now, once again, if you want to maybe just see what we've done here, let's take a look at that function, but just only over that little quarter of a disk and see what it looks like in Maple. And so, example 2 here, I've done a very similar sort of technique. Define the function g as a function x squared plus 2y minus y squared, but only over that 1/4 of a disk. X is greater than or equal to 0, y is greater than or equal to 0, and x squared plus y squared is less than or equal to 4. It's undefined everywhere else. And I'll plot that so we can take a look here. Now the origin, we just maybe rotate around here, is at this particular corner. If you look straight down, you should be able to see it looks like 1/4 of a disk. And along the line x equals 0, we have a parabola. You can see where we had one critical point on the function, right at the point x equals 0, y equals 1, but it's actually not a local maximum because it is at the lowest point of this cross section heading up along the line y equals 1. We have two minimum values at 2 of the vertices, and our third vertex is not quite the highest, it's just a little bit below this maximum value which occurs along the boundary edge. That maximum value there is at 4.5. So you get a pretty good sense of what we've just maximized and minimized on that region. Now, optimization is an important application of differential calculus. And so far, we've really only just scratched the surface. We were taking a look at maximum and minimum values of just some random function over a region I've given you. But if you actually are interested in optimization, then you're going to be looking at applied problems where you may be trying to minimize some kind of cost function subject to certain requirements of the application. So you can maybe try to picture where this is going and why these are useful tools. But stay tuned, we're still going to be taking a look at optimization in yet another video where we will try to take a look at some applications and maybe a slightly different technique for how to optimize some function given certain requirements. Not just within some geometric region, but just with certain real-world requirements, and we'll see how to solve that in the future. So stay tuned, thanks for watching, and I'll see you in the next video.